Ingamana, ingareo, ro rakatira ma, tanakoto, tanatato katoa. Norera, ko waio, ko Harleen Hain, takawingawa, ko te tumuaki o te whare wanaka o a tako aho. Namihi nui kia koto, norera, tanakoto, tanatato katoa. Good evening, everyone. My name is Harleen Hain, and I am the Vice Chancellor here at the University of Otago. And it gives me great pleasure to welcome you to this inaugural professorial lecture for George Dias. These lectures are always a time of immense celebration for us here at the university, and it's fantastic to see so many people here who are going to take part in the celebration of George's promotion to professor. On behalf of the university, I would like to extend a particularly warm welcome to the members of George's family who are here with us this evening. His wife, Rohini, his son, Asela, and his sister, Malkanthi, who have traveled here to be with us tonight. The presence of family is always such a clear indication of how important these events are. Now, in addition to members of George's family, as I look out on the audience, I see staff and students from throughout the university, and I'd like to also extend a particularly warm welcome to our Chancellor, Dr. Royden Somerville, who is a regular attendee of these very important events. To each and every one of you, no mai, haramai, welcome. So, to set the stage for tonight's event, I think it's really important for us to just spend a moment and reflect on the fact that the path to professor here at the University of Otago is not an easy one. In order to be promoted to the rank of professor, the individual must demonstrate excellence in teaching, in research, and in service to the university and the broader community. In terms of research, George is a world leader in the field of biomaterials. He has an outstanding track record of research publications, of patents, and of extramural funding. George is also an outstanding classroom teacher and a very popular postgraduate supervisor. And last but certainly not least, George has provided exceptional service to his department, to the university, and to the wider research and academic community. George, on behalf of the University of Otago, it gives me great pleasure to personally congratulate you on your very, very well-deserved promotion to professor. Over the years, I have certainly valued not only your teaching and your research and your service, but I've also valued your incredibly positive attitude towards everything that you do. Namihi nui ki akwe. I will now call on Professor Vernon Ward to tell us just a little bit more about George's academic journey to professor. Norera, tanakoto, tanatato katoa.
Thank you, Vice-Chancellor. Tēnā koutou katoa, hame nui tēnā kia koutou. Welcome, everybody. It's really nice to see you here this evening. The audience is looking particularly anatomical. So one of the privileges of my role as Dean of the School of Biomedical Sciences is I get to introduce our new professors to the audience, and it's a real privilege to be able to do this. And so I have the privilege of introducing a little bit about George Dias to you today. He is, as already stated, a very valued member of the Department of Anatomy, where he's in the clinical anatomy team. And again, his input is really broad across the spectrum, and that's very much appreciated by everybody. His background, I find particularly interesting and fascinating. He graduated originally with a Bachelor of Dental Surgery from the University of Sri Lanka in 1977, and then he had a number of professional qualifications since. These include a Master's of Dental Surgery, and he is training in oral and maxillofacial surgery. So he's very well qualified, and there's a number of other qualifications in amongst that as well. With that broad training background, as you'd expect, he has a range of professional appointments. He started as a house officer in the Dental Institute in Colombo. This was a series of progressive steps there. He then moved on and did a lot of work in the Sri Lankan Air Force, eventually becoming the consultant dental surgeon for the Sri Lankan Air Force. He spent some time in the UK. We might have to share some stories of Southampton. From then he decided to do PhD studies, and he came to Otago for those PhD studies, receiving his PhD in 2003. He started his work in life here as a junior academic and has then progressed through the academic ranks of the university and again contributes across the spectrum. The one area I'm going to focus on for this introduction with particular note is this work in and around the translation of research. He has a very applied aspect to his scientific research. He looks at biomaterials in particular. He has a very inquiring mind and he looks to how do you apply this. So I'm not going to... That wasn't me. So I'm not going to go preempt his talk because I think I don't want to take any of the thunder away from what he's going to present to you, but he contributes in the area of high-value functional foods into our technology industries. And again, it's all his work that he's going to see tonight is around how you translate. So he's been funded by numerous agencies. These include the Health Research Council, the Ministry for Business, Innovation and Employment. I always want to say everything, but employment, AgMart, and the wool industry. His research output you'd expect of a professor, and commensurate with his translational research focus, I draw attention to the actual real impact and commercialisation activities that he does. His patents have been bought by companies. They've received royalty payments, so the real is that a company established based on the work that he does, and then I know there's further negotiations and commercial opportunities in the pipeline. He's a scientific advisor and a consultant to industry and to government bodies. And along the way, he's never forgotten his roots. He provides expert translation in Sinhalese for the police, the Ministry of Justice, and indeed for the University of Otago. So there are many things I could go on with his career, but to do so would take away from him actually speaking to you. And so we need to move to that point. And so for this inaugural professorial lecture, Professor Dias will explore his personal history. He's going to move into translational research and some of the ideas that he's developed, the securing of intellectual property and the commercialisation of that research. I'd now like to invite Professor Dias to present his inaugural professorial lecture entitled Anatomical Adventures with Making Faces, Bone Building, Wool Foods and Corroding Plates. Nō reira, tēnā te mihi kia koutou katoa. Tēnā koutou, tēnā tātou katoa.
They switched on. Yes. Thank you, Professor Hain. Thank you, Professor Ward, for your kind introductions. I'm humbled by your words. Thank you, everyone, for your presence this evening to share with me this special occasion in my academic career. And also thank you to my family who's been here, my wife, Rohini, Asela, and my sister. I'm going to tell you about the journey that I took to arrive at this position. Okay, so a lot of people helped me along the way. A lot of people worked with me. My mentors, my colleagues, collaborators, and also not forgetting the students. So I'm going to acknowledge them as I go along. And also, I'm going to show you how these words in the title of my talk came to be. I was born in this island here in the Indian Ocean. It was called Ceylon, where the world's best tea come from, Ceylon tea. And the place of birth was, it was close to Colombo, the capital, somewhere here. And so I grew up in Colombo. This is Colombo in the 60s and 70s. So there are some double-decker buses, etc., very British. And in 1972, the country changed its name to Sri Lanka. And this is Colombo today. It has gone very big, and it has gobbled up my home village. My home village is somewhere here. Now it's part of the city. Yes. And now I'm going to share with you my family album. So this is my ancestral home from my paternal side, where I spent a number of my early years. By the way, now this doesn't exist. In this place, there's a tower block, apartments have come up. These are my grandparents, paternal grandparents. You can see very Victorian at their wedding, at his homecoming. And these are my parents, my late mom and dad, Sheila and Herbert. This is yours truly, the mop of hair. And me with my two brothers. There are altogether 7 of us. My 2 brothers, and this is my maternal ancestral home, where I spent a lot of my early years in this house. Again, it also doesn't exist anymore. We're looking very pious at my first Holy Communion. And I also played in a band. I'm sure you don't know. I played in a band. And would you believe this band is still going strong? And this is a few years ago. And that's the day. So maybe I would have had a career in like the Bee Gees or something like that, playing in this band. Not as good as Bee Gees, but... we also went through our Afro stage. This is my sister and my 2 brothers. And my dad was a GP in London at that time. And I had to trim my Afro down for my wedding. Maybe Rohini has something to do with it. This is the 7 of us. I got 4 sisters and 2 brothers. And one of my sisters are here. Malkant is here. And this is my family, Rohini and Asela. This is my school that I went to, St. Joseph's College. And in fact, Black Caps just finished their tour of Sri Lanka. The captain, cricket captain, and I think 3 players come from this school. So I'm just bragging a little. Then I entered the university, as Professor Ward mentioned, University of Peradeniya. It's a very picturesque campus, similar to our Dunedin campus. That's the registry building, the amphitheater, and also when the flowers are blooming, it's like that within the campus. The old medical faculty building. So I did my first degree, my dental degree at the Faculty of Dentistry. Then I had my clinical training first at the National Dental Hospital, the Dental Institute, Colombo. Did my postgraduate degree at the Postgraduate Institute of Medicine, University of Colombo, where I obtained my Master of Surgery, as well as later on the board certification in maxillofacial surgery. After that, again, I had my surgical training at the National Dental Hospital, as well as the Colombo Cancer Hospital. Then I went off to UK and did my also training at the Canisburn Hospital. This is a specialized unit where they do only plastic surgery and maxillofacial surgery. These are some of the staff and the trainees. They also run a number of training programs. So these are after one of those training programs. I'm in the back. You can see me now peeping. That's me down there. And also I had a beard once. And that's me doing a surgical procedure, I think most probably at the cancer hospital. I want to thank these 2 gentlemen. I'm very grateful to Mr. Kershid Moose and Mr. Tony Gabriel. In fact, I trained under them. I learned my maxillofacial surgery under them. In fact, I must apologize. This is the only photo I could find of Tony Gabriel. I can assure you he was much more mature when I trained under him. This is, I think, when he was about 18 years old. Then I came to New Zealand, joined the anatomy department, started a PhD on looking at the temporomandibular joint. This is coming from my clinical background. My supervisor was first Phil Horton, Associate Professor Phil Horton, but about 1 year into my PhD, Phil decided to retire. So then, and I was supervised by Professor Gareth Jones from then onwards. So the topic of my PhD was the temporomandibular joint. I was looking at the temporomandibular joint because this is a major, temporomandibular joint disorders are very common. About 10% of the general population suffers from some degree of TMJ dysfunction. So I was interested in looking at the joint because it's a major public health issue. Now, one of the questions I wanted to answer was that whether the joint has a specific morphology, specific shape, as it is described in the textbooks. Or does the shape of the joint changes with the functional environment? Because at that time, people with TMJ dysfunctions, we used to go into the joint and try to chisel off the so-called perfect morphology. So I want to question that whether it is correct. Nowadays, we don't do it anymore. So for this part of my study, I did an animal study. I used the kuni pig. It's a small, rare breed of, not rare, it's a breed of pig found in New Zealand. It's quite small and very docile. I think to my knowledge, this is the first time the kuni pigs have been used in a research project. Because as you know, the American mini pigs are extremely expensive and almost nobody can afford to use them. So I've been trying to advocate using kuni pigs, and I'll be starting another project very soon. So I divided the animals into two groups. One group of animals were kept on a soft diet, like porridge diet, and a hard diet group, which received the same amount of nutrition, same amount of food, but in the form of hard pellets, where they had to crush and chew the food. So they kept the animals for 7 months on these two different diets. So as you can see at the end of the study, the weights of the animals didn't vary. So that means they had the similar amount of nutrition. So during the study, I injected the animals with vital stains. So these are stains that mark the bone that is being deposited at that point of time, so that you can later on see the amount of bone that has been deposited. So there were 3 injections, 2 doses of oxytetracycline that stain the bone later on under the fluorescent microscope. It glows green, and alizarin red, which glows green. So there were 2 tetracycline, or oxytetracycline, and alizarin red dose. And also we use this technique, backscattered electron imaging, to quantify the degree of mineralization. So the results, what we found was that the hard diet group had significantly more bone deposition in the temporomandibular joints compared to the soft diet group. We also found that the degree of mineralization in the hard diet group was significantly higher compared to the soft diet group. So this was published as part of my PhD. So I moved on. At the end of my PhD, my bioanthropology colleagues in Coimbra, University of Coimbra in Portugal, it's a very old university, about 800 years old, they invited me to join them, to collaborate with them on this area of research, the facial approximation. The reason they called me is not because I knew a lot about this area, because of my expertise in the craniofacial anatomy. So this facial approximation is a technique where you construct a face on an unknown skull for forensic purposes. If you got an unknown skeleton, you want to make an identification, you can put a face on the skull, and that may trigger the identity of the person from a witness. That's the main reason, the forensic facial approximation, but it is also very popular with the general public, where you can put faces on historical figures such as Cleopatra or Tutankhamun. And so it is very popular in programs such as Meet Your Ancestors kind of thing. So that is this area. And I'm very thankful to Carl Stefan. Now he's at the University of Queensland. He was extremely helpful to me at the start of introducing me to this area of research. So I'll show you a few cases that we did. This is the Egyptian mummy that is exhibited at the Otago Museum. And the museum staff has CT scanned the mummy. And these scans were made available to me a long time ago. This is about mid-2000. These were not very high resolution CT scans, but we used a 3D software program to extract the digital image of the skull of the mummy. And although there are a lot of artifacts, the details on the bony details I thought it was sufficient to do a facial reconstruction. Then we 3D printed the skull. Now, this was in mid-2000s. At that time, this was cutting-edge work. In fact, it was not even called 3D printing. It was called rapid prototyping. And I had to go to one of the specialized companies in Christchurch to get this done. So we got the skull. Now, to put a face on on a skull, you got to know the soft tissue depths at different positions on the facial skeleton. Now, these soft tissue depths are available in the literature. People have measured these soft tissue depths from cadavers, etc., for different ethnic groups. These are available, the averages, such as this. But we thought this is not very scientific, especially for a court of law to make identification. So therefore, we developed a model. I worked with my colleague, Professor Pemachandra from Accountancy Department. We developed this model, a model to predict the soft tissue depths based on the bony measurements of the skull, the craniometric measurements. So first we trained this model using cadaveric bone measurements as well as soft tissue measurements. And then we tested the model to find out its accuracy. It was pretty accurate. So then we put in the bone measurements of the mummy skull, and it predicted the soft tissue depths. So we used these measurements to do the reconstruction. So these I set about doing. I will not go into too much detail. So here I'm drilling holes at different points on the cast of the skull to position the pegs to indicate the soft tissue depths, and also the position of the eyeball, the nose projection. All that was done based on anatomical and surgical, especially plastic surgical principles. Same principles went to getting the mouth width, the lip thickness. The position is very important, getting the position of the eyelids, the nose width, and also the muscles of facial expression, including the glands found in the face, parotid gland, etc., buccal pad of fat, all that. So I used all that and reconstructed the face. Then the Otago Museum commissioned a makeup artist to give the skin tone and the eyebrows and the hair. In fact, the hairstyle and the skin tone came from the painting on the sarcophagus of the mummy. From that, it was generated. Of course, it created a lot of media interest, and the making faces in the title of my talk come from this media article. I did a few other cases. With my colleagues in Germany, from University of Dusseldorf, we did a facial reconstruction on a forensic case, unknown skull. Also, I worked with my colleague and friend, late Professor Jules Kieser. Jules was contacted by the New Zealand police regarding this skull, but later we found it is not foul play. But as part of Charlotte Oscombe's postgraduate project, we did a facial reconstruction, and also Stephen Swindle also assisted on this project. And also, finally, my colleague Handan Ustunga from Turkey, University of Anadolu, she sent me a cast of this skeleton, about 2,500-year-old skeleton. And we did a facial reconstruction. This was part of Louisa Bailey's postgraduate program. And we did the reconstruction. These are the members of the team. And of course, here we used some newer material at that time, silicone, etc. And this face was sent to Turkey. It was exhibited in an exhibition in Istanbul at that time. So at this stage, and I know Louisa is carrying on in this area of research, because at this stage I changed the focus of my research. I started doing more translational research. Now, what is translational research? There's no difference. Now, in the university, we do research, and then we publish our research, disseminate the information to improve the knowledge. Now, in translational research, you just add an additional step. Before you publish, you try and capture if there's any intellectual property. You capture the intellectual property and then convert that the knowledge into a product or service to assist, for example, in clinical practice. You translate your findings to clinical practice to improve the health of the people. Okay, that is translational research. And also, you can commercialize this, your finding, because research costs money. Because the money, somebody has to pay. So if you can generate more money, you can do more research. And it's good for the university also. So that's translational research. So we, in the universities or in other research organizations, we do a lot of basic research. but only some of that basic research is suitable to be translated. Out of that, again, only a small proportion will ultimately end up as a product or service. So not every time you come up with the idea doesn't mean that you will be successful with a final product or service, but it's worth the attempt. So in a nutshell, commercialization is where you convert your research, your discoveries into products and services. You can do this by several means. You can license your invention to the commercial sector for royalty payment. Or with the university, you can establish a startup company. You add more value to your discovery before you transfer it to the commercial sector. Or you can sell it off outright to the commercial sector for a lump sum payment. So that's in a nutshell about the translational research I got into. Now some of those ventures that I took part in. Building bone from sheep's wool. As you know, we have a lot of sheep in this country. In fact, 10, 15 years ago, we had more. And we are the second largest wool exporter in the world. But unfortunately, about 60% of our wool clip is low-value wool. It commands very low market price. Okay, especially the medium and coarse wool has very low market price. It's only the fine fiber has a good value. So one of the aims of our project was to add value to this cheap commodity. In this venture, I collaborated with Rob Kelly, Dr. Rob Kelly. At that time, he was working for Wool Research Organization of New Zealand. That's the successor of the old Wool Board. So all the wool farmers are members of Wool Board. It's like a cooperative. So now it's called Wool Research, RONS, Wool Research Organization of New Zealand. So I collaborated with him. Now about keratin. Now wool, hair, horns, hooves, including the rhinoceros horn, is all made of keratin. It's a protein. It's a fibrous protein, similar to collagen. So proteins are made of amino acids. Okay, so these amino acids come together, forms chains, peptides, polypeptides, and form proteins. Now keratin protein is very rich in the sulfur-containing amino acid cysteine. So now these sulfur groups forms very strong disulfide bonds, covalent bonds within these protein chains and between chains. Now hair, wool, horns, etc. get their strength due to these disulfide bonds. And this is one of the reasons you can't, because wool is 95% protein, but we can't eat it because of these disulfide bonds. You can't digest it. Of course, there are funguses which can do it. So when you look at a wool fiber, these are the constituents down to the peptide chains. For our first project, we extracted this group of proteins, the intermediate filament protein, so certain molecular weight. So we extracted that protein. Now, keratin is a very versatile biopolymer because you can cleave these disulfide bonds and solubilize. So you can make the keratin soluble. And you can reverse this reaction. You can reform these disulfide bonds. And you can control the formation of these disulfide bonds. You can control the polymerization. By controlling the polymerization, you can make a number of different products. A lightly polymerized state, you can produce hydrogels. You can produce membranes. You can extrude into filaments, electrospinning, etc. Or the highly polymerized state, you can produce strong plates and screws. So it's a very versatile biopolymer. So our first venture was developing a bone graft substitute, keratin-derived bone graft substitute. So what is the reason for this? Because every day New Zealand spends a lot of money in the health sector treating bone fractures. Now, number of these fractures requires bone grafts. Now, there is a limit where you can harvest bone from a patient, autologous bone. So there is a huge need for bone graft substitutes. So that's the reason that we got into this area. So we developed this porous keratin scaffold, this porous scaffold with regular pores. Okay, these are not random pores because bone cells do not like to get into dead ends. Okay, it requires these channels running through. So we produced this porous scaffold, incorporated the hydroxyapatite, that's the mineral found in bone, to mimic cancellous bone. Then we carried out the standard in vitro investigations to make sure it's non-toxic, start with, biocompatible, osseointegratable, and the viability of osteoblasts, all that we did. Then we implanted this scaffold in the long bones in the hind limbs of sheep. In fact, we did 3 sheep trials. In fact, this was funded by the Wool Board. What did we find? Now, you can see this orange-colored septa, that's the keratin scaffold. The pink material, that's new bone. Now, at 4 weeks, you can see the new bone is growing into the keratin scaffold. And also, this section doesn't look angry for the histologist. There is no lymphocytes, there's no giant cells, etc. So this is, and also now you can see the bone growing into the scaffold, and also you can see bone growing along the septa, keratin septa. Now here, the keratin scaffold is acting as a template for new bone regeneration. So this is targeted bone regeneration. That's a really good thing. You can target how the bone, you want the bone to form. So at 8 weeks, you can see most of the keratin is gone, replaced by bone, okay? And so also what we found was that our keratin scaffold was behaving almost like autologous bone. So we were very excited by these findings. So we captured the intellectual property with a PCT, international patent, and then jointly with RONS, we lodged national patents, including a US patent. So at this stage, we transferred the IP to the commercial sector. Now this intellectual property is owned by Keraplast Technologies. It's a US biomaterials company, but they still manufacture their product. There are a few products in the market in Lincoln, in New Zealand. And also I know the Wool Board is trying to buy back this IP. We want to bring it back to New Zealand. So after we captured the intellectual property, we published all this data. So this is a good, clear case of you can have the cake and eat it. We got all the publications, plus we got intellectual property. It's just that we had to slightly delay the publication until you capture the intellectual property. So this is where the woolly and the bone builders in my title of my talk comes from. So I'm just showing you how this title came to be. I also worked on another bone graft material. This time, cattle bone-derived bone graft material, bovine-derived xenograft. Now, in this project, I worked with my colleague at the University of Waikato, Michael Mazzolo, and this was part of Dougal Leard's PhD program. Now, the inorganic part of the bone, inorganic component of bone, which is hydroxyapatite, the inorganic part of cattle bone and human bone is very similar. Okay, it's hydroxyapatite. And morphology is also similar, the porosity, etc. And also it is not pure calcium phosphate. It has all the other trace amounts of other materials, such as carbonates, calcium carbonates, sodium salts, magnesium ions, fluoride, silicates, etc. So this is a good match for us. And there's other reason is that, as we know, in New Zealand, we have an extensive meat industry. And bone is a waste product. So this is a venture we want to add value to this waste material. So briefly, what we did was we, of course, cut the bone into cubes, pressure cook it to get rid of essentially the fat in the bone. Then we sinter it at very high temperature, 1,000 degrees, to burn off all the organic phase of the bone, resulting in the inorganic phase, which is hydroxyapatite. But there's a problem when you remove, especially the collagen fibers from bone, it becomes very weak. This hydroxyapatite is extremely fragile, very poor mechanical properties, especially tensile properties. So what we did was we infiltrate these scaffolds, these hydroxyapatite scaffolds with polymers, natural polymer, chitosan, and synthetic polymers such as polycaprolactone. So these are biodegradable polymers. These polymers break down in the body. So we use these polymers for two purposes. One is to improve the mechanical properties. The second reason was to improve biological properties. And again, we captured the intellectual property here with a PCT. And University of Waikato established a startup company, Grafts Limited, in 2007 to commercialize this product. So but we kept on improving this material. We want to improve this material because we knew that there is scope for improvement. So this work has been done as part of Jitendra, my former PhD students, Jitendra Dr. Ratnayakar's and Niranjan Ramesh's PhD programs. We are improving this material. So we added 2 additional steps for this process, the manufacture. We added a step where we treat the bone cubes with sodium hydroxide for 2 reasons. One is to more efficiently remove the fat from bone. Second is the sodium is to destroy abnormal proteins such as prions, so that later on we can guarantee that our product will not transmit any diseases. Second is that we added another step, subcritical water extraction. Now, water at very high temperatures, about 180 degrees under pressure, you can keep it as water. It becomes an excellent solvent. So we use this subcritical water extraction to more efficiently remove organic matter from bone. So that resulted in very pure hydroxyapatite at the end. Of course, we characterized it to make sure it has not changed. It has not changed from hydroxyapatite because it can change into other phases of calcium phosphate. So we did all this characterization and also image to make sure the pore structure is maintained. Then we did another treatment. Now, when you look at the hydroxyapatite molecule, you can substitute the calciums, the phosphate, and the OH groups with other ions, such as silver, magnesium, silicon, etc. So now these substitutions are done to improve the mechanical properties and the biological properties. In fact, there's one product where it's only some of the OH groups have been, phosphate groups have been replaced with silicon, and it's a multi-million-dollar business. It's called Actifuse, done by academic in UK. Now it's a massive company. It exponentially improved the biological properties of hydroxyapatite. So therefore, now these substitutions into synthetic hydroxyapatite has been done. There are a number of products in the market, but the novelty in our project is that we did substitution for natural hydroxyapatite. So that's the novelty. And so this is the product that we ended up with all these properties. I will not go into detail. So, but our product is comparable to these products which are already in the market, comparable or superior, especially like BioOS. Now we buy hospital and maxillofacial surgery, they'll use a lot of BioOS. It's about $6,000 a pack. And we think that our product is similar or better than BioOS. So we are in the process of capturing the intellectual property of our product. So moving on to another project, developing a dietary protein. Now the knowledge, the know-how comes from our previous work developing the keratin-based bone graft material. So not that I suddenly decided to go into food science. It's just that we translated that knowledge into another area, keratin-derived protein powder. So this work was done with my colleague, collaborated with my colleague, Aladdin Beckett from Department of Food Science. And I must acknowledge these people. Eric worked with me at the very beginning. I'm sure, Eric, you remember. And we had a time trying to get some funding. People almost laughed at us. And also Lux Selvanesan and Harold Bernard, they also were part of the team. So we came up with this protein powder. So why another protein? because there's a reason, our reasoning was this. Now 67% of protein in our diet comes from traditional animal products. So there's a problem. There's a need for a new protein because of these problems. Increased production cost, animal welfare issues, environmental issues with this intensive farming, health concerns with consuming fat because protein comes with fat, animal protein, and also the food safety issues, antibiotics, et cetera, et cetera. So there is a need for novel proteins. So in our project, what we did was we found a method to cleave these disulfide bonds. Now, if you break these disulfide bonds, you can make keratin digestible, okay? Because having these disulfide, that's the reason, these strong bonds is the reason that the proteases can't break the keratin molecule down. So we cleave these disulfide bonds and make the keratin digestible. We did that without using harsh chemicals. We just used food ingredients. So we treat the wool in the presence of water and expose it to high temperature and pressure using microwave energy. And in the presence of food acids, you convert the wool get converted into this emulsion milk-like product. And this can be separated into 3 fractions, a soluble fraction and 2 insoluble fractions. So we use these 2 insoluble fractions, dry it, and we get this powder similar to whey protein or soy protein, etc. Analyze the amino acid profile. It's quite a complete protein. It has all the essential amino acids, very rich in certain amino acids, low in some other amino acids such as lysine, methionine is a bit low. Now, then we had the problem. Now we had to find a way to deconstruct the wool fiber. You can't, because what we did was on a laboratory bench, so we had to find a way to do this in a bigger scale. So I worked with this company, Microwave New Zealand. It's an Auckland company with very closely with John Holdham and Joachim Rowing. We had to design from scratch because this kind of thing didn't exist. So we had to design and fabricate, build the microwave machine to deconstruct the wool fiber. So initially we built a prototype machine which can handle about 100 grams or hundreds of grams of wool. Later we scaled it up because part of this MB grant we had to show you that this can be scaled up. Built a bigger machine, which can handle kilograms of wool at a time. Using this, we produce about more than 125 kilograms of this wool protein powder for the subsequent investigations. And these are housed at our Soes Bay facility, Otago facility. These machines are kept there because they generate a lot of microwave. It can disturb the Wi-Fi supply if you do it close to the university. Then we compared the wool-derived protein with the other bulk protein which are in the market, like whey protein and soy protein. You can see the keratin-derived protein is very rich in certain amino acids, arginine, cysteine, glycine, and also it's rich in the mineral selenium. Now, as we know, arginine is important as a precursor for nitric oxide, the body part, that's for vasodilatation. So vasodilatation is important for muscle recovery after exercise, to recovery of muscle for athletes, and also in type 2 diabetic patients, to improve the tissue perfusion. Whereas cysteine, glycine, and selenium, these are all cofactors in the body's built-in antioxidant mechanism to mop up the free radicals. Okay, so therefore these are important ingredients to have in our diet. So this protein has all that. We analyzed the protein content. It is a very rich protein. It has about 86% protein. Later we improved it further. So it is comparable to the premium proteins in the market, such as whey protein isolate, the more expensive whey protein. Then we want to test whether this protein is bioavailable. Can this protein be digested, absorbed, and utilized by the body? So we did a number of animal trials. mouse trials, 28-day mouse trial. The control diet contained casein protein. That's the gold standard protein. And the experimental diet had keratin-derived protein. You can say at the end of 28 days, there was no significant difference between the two animals groups. So that indicated that our keratin-derived protein is being digested, absorbed, and utilized by the body. We also did the 95-day, much longer rat growth trial with similar results. Then this confirmed that this protein is digestible and utilized by the body. We also wanted to show that the selenium, and also, by the way, it also contains zinc, that the selenium and zinc found in the keratin protein is bioavailable because it could be bounded and which may not be able to be digested and absorbed. So we formulated a special diet, a rat diet, a low selenium diet. And when the animals on the low selenium diet, their blood selenium levels, serum selenium levels dropped and stayed low. But the animals supplemented with the keratin protein, their selenium levels recovered. Same with the zinc. Control animals, the zinc level dropped and stayed low, whereas the experimental animals with KDP, it recovered. So this proved that this selenium and zinc found in the keratin protein is readily available in the diet, bioavailable. So this is our pitch, high yield. In fact, most of the protein we lose only about 15%. That also could be recovered. It's too expensive to recover that. So, or practically all the wool can be converted into this protein. It's a high quality because it has all the essential amino acid, and it's novelty, fat and carbohydrate free, and quite versatile. It can be incorporated into different foods. Relatively cheap to produce, very competitive price point compared to whey protein and soy protein. We have captured the intellectual property for the process. We captured the intellectual property, and recently we transferred the intellectual property to Wool Research Organization of New Zealand. That's the Wool Board. So I'm very happy that it's staying in New Zealand, and now I'm working with them. We are lodging the national patents to protect the IP in European Union, United States, etc. So this is only the process that we captured. We also tested this protein for its acceptability. And so here I worked with my colleague, Aladdin Bucket at the Department of Food Science, and we incorporated the protein into different foods, into muffins and into muffin. You can't knock it off, is it? Maybe you have to crush the phone. We incorporate the protein into muffins and corn chips. Into muffins and corn chips, 4% keratin protein, 8% keratin protein, and we tested it using volunteers, about 120 volunteers, and they scored the texture, the color, and the flavor. As you can see, especially keratin protein in corn chips was scored very high, almost comparable to the control. So it's acceptable by the public. We also did another human trial with type 2 diabetic patients, both male and female. We had about 36 participants, and they went through a 14-week program, and they were provided. They took about 16 grams or 17 grams of keratin protein per day. I have to apologize. I'm not in a position to give details about this because we are in the process of capturing the intellectual property, because this is in fact, we found some very interesting results. So hopefully once it's captured, I will be able to talk to you about it. And now, of course, here I work with my colleague, Professor David Rowlands from Massey University, doing this human trial. So finally, the food off sheep's back comes from all this protein stuff. And finally, I've been working with my colleague Mark Steiger at University of Canterbury, the Department of Mechanical Engineering. We have been doing this project for now about 10 years. The project got slightly delayed due to the earthquake and the laboratories got affected. We are now bone fracture. Now I want to acknowledge Alexis, Alexis, she was a postdoctoral fellow. She worked with us at the initial stages of this project. And Nick Kirkland and Jemima Walker, they are PhDs contributed to this project. Now, when bone fractures are commonly treated with bone plates and screws. Okay, it's a very common method of treatment for fractures to fix and immobilize the fracture. So now the material, these plates and screws are made of permanent materials such as stainless steel, titanium, and other types of alloys. So, but the shortcoming is that once you put this permanent material, they stay inside the body. Once the fracture is healed, still the plates and the screw stays on. If you want to remove it, you have to do another second surgery, go in and remove it. Sometimes it's almost impossible to remove, especially titanium, because bone grows over these plates and screws. It's almost impossible to remove it. So, what we are developing is a metal alloy which is as strong as titanium, but the beauty is that it will degrade and break down in the body, and the body will excrete it through the kidneys and the gut. It's a magnesium alloy. So we think it will make a revolutionize this area of research, this treatment. And also there are additional advantages. Magnesium alloy, the mechanical properties of magnesium alloys is very close to that of bone. Now, with another problem with these very strong metals is that it retards the new bone formation. If you put stainless steel, the steel carries the load, bone will never recover. So, but with magnesium, because the mechanical properties is closer, it will stimulate new bone formation, so you don't have the stress shielding. And another advantage is that new bone requires magnesium. So as this plate breaks down, it feeds the bone formation. So it's a win-win in all aspects. So that is our setup. So you have to be careful when you melt magnesium because it's explosive. The whole place can go up in fire. So you have to do it under argon inert gas environment. After we cast these alloys, we treat them thermomechanically. What we do is that the cast alloy is extruded through narrow openings into rods and plates. By doing so, you can improve the mechanical properties and also the corrosion properties tremendously. You can almost you can have a completely different properties in your end product by doing these different treatments. Now, this work is done as part of Ryan Wilkes' PhD program, which we are supervising Otago and Canterbury. So altogether, we produced about 60 different magnesium alloys. Now, from these 60, we had to finally come down to one for our device. So initially, what we did was we screened them by looking at their biocorrosion. We exposed them to simulated body fluid and assessed their corrosion. Using that, taking that into account, we narrowed it down to 17 alloys. Now, these 17 alloys, we checked their mechanical properties as it corrodes, as it degrades in the simulated body fluid. Taking this criteria into account, we reduce it down to 4 alloys. Two magnesium calcium alloys, magnesium manganese alloy, and a magnesium zinc alloy. We tested this with cell culture methods, compatibility, cell proliferation, cell viability, using fibroblasts-like cell lines and osteoblasts-like cell lines. And also we implanted these alloys subcutaneously as well as intramuscularly. Now, this is a novel method which we developed as part of Jemima's PhD. Intramuscular location is a far more biodynamic location compared to subcutaneous. Now, a lot of others are using this method. So we implanted them and then looked at their interaction with the surrounding tissues, both positive and negative. Were there any inflammatory reactions, any giant cells, lymphocytes, or angiogenesis positive? And also we were looking for when magnesium degrades, it produces hydrogen gas. So we want to make sure that there's no excessive amount. At a certain rate, the body can handle it. So it shouldn't want to be too excessive. In fact, if I can show if I have the time, then there's nothing wrong, nothing new about this research. 100 years ago, they tried magnesium. At that time, unfortunately, they couldn't get pure magnesium, so they put into patients, and patients blew up as balloons, and that's why it went out of fashion 100 years ago. So we resurrected this knowledge. So by doing this, we narrowed it down to 2 alloys, and we implanted these alloys in the long bones in sheep, looked at their interactions, the degradation intraosseously, the bone to implant contact, looked at histologically how it reacts with the surrounding bone. So taking all that into account, we selected 1 alloy, magnesium zinc alloy. Now at this stage, these two, Bartosz Nowak, he's a design engineer, joined our group. And also now we have Anton Good, he's doing a PhD in this aspect of the study. So we spent a lot of time modeling these devices. Okay, we had to make sure these devices will not fail, the finite element analysis, all that, to make sure that these screws and plates won't fail. And then we thought that we had to send it to Germany to get these mini plates and screws made. But we skilled ourselves. Now we are manufacturing it here, got high precision lathes and milling machines. So we are producing these plates and screws, tested them for biocorrosion of the screws and plates, ability to insert them into pig bone, in abattoir bone. And also we tested these plates and screws on pig heads received from abattoirs. We carried out osteotomies on the cheekbone, zygomatic arch, as well as the supraorbital margin, because these are common areas for fractures, and tested these. And in another few months, we will be starting an animal trial with pigs, and they'll be assessed for 12 months to assess the bone healing as well as the degradation of the plate. So that's my journey. And as you can see, this took a lot of metal. And I'm very thankful for my colleagues, my students, and my collaborators who made this journey enjoyable journey. Before I finish, I would like to introduce another fellow Sri Lankan. Now, he came to New Zealand long before me, about 150 years ago. That's a Sambadia. I took this photograph myself. Sambadia was introduced to New Zealand from Ceylon in 1875. And with that, thank you very much. Bome Stote.
Well, thank you, George. My name is Lisa Matasu-Smith. I'm the head of Department of Anatomy. And it's a big job, it's a big department, it's an incredibly diverse department. And I have to say, one of the first things that I did when I took up this role was try to get my head around the diversity of the department and what people did in the Department of Anatomy. I knew my colleagues, but I didn't really know that much about what they did. And clinical anatomy was the group that I started working with first, and this included getting to watch George, particularly in teaching in the DR, in the dissection room, where I was teaching Med 2 and 3 students, and seeing the enthusiasm that he shares with the students, and then watching them interact was truly a lovely thing to watch. And then hearing your interactions with the PGDIP, the surgical anatomy students, the young doctors who are coming and who George has been organizing this program and training the students, and hearing their feedback and watching that interaction. I think, you're an amazing researcher, as we have heard, but certainly an outstanding teacher and a great colleague.
I have to say. But one of the real high points of being the head of department is getting to participate in these IPLs. And I think George demonstrated both the diversity of research that gets done in the department, but really the fact that he takes that research from that basic knowledge all the way through translational and developing new products. But I would expect that you all also enjoy the personal aspects of these IPLs and getting to know a little bit more about the background of our colleagues, of our friends, and hearing about their families, hearing about how they actually got to where they are today, which is truly fascinating. It makes you realize things, that you never knew about your colleagues. I knew about your love of cricket, but I didn't know that you were a rocker, and we're going to have to get you to display some of that expertise for us sometime soon. I was thrilled to hear that somebody else has studied kuni pigs. I've done the sequences of kuni pigs, so again, we've got much more in common than our ability to have an afro, and your involvement in biological anthropology, which is always fun to see. But I think really we can all appreciate that George and the talk that he's given us today, this IPL. Just shows how he really not only thinks outside of the box, but he would probably create a whole new box out of biomaterials that were tasty and like corn chips. So this truly is an amazing skill and something that we value hugely, both in the department and in the university. And so I would just like you all to join me in thanking George for this amazing IPL and congratulating him. And we have a small gift. So, George, thank you so much.
Thank you very much, Lisa. Thank you. Thank you.